The very last thing we would need to discuss, and this is more conceptual than anything, how light or heavy does an object feel at various locations in its circular path. So if we look at this, we want to look at the concept of weight. I put it in quotes in terms of what people consider to be their weight, what they feel as their weight, versus, this should say weight, versus the actual weight, the force of gravity acting on an object. If we take a look at this diagram, you'll see that any object has a force of gravity. It has a weight. That's what we officially call weight. It's the force of gravity. What people feel, though, as weight, in quotes, what they tend to think of as their weight, is actually that normal force. The normal force from the ground is what your average human being feels. So when you think about, you're tired, you've been carrying your weight all day, you don't actually feel your weight. You feel the force that acts on you. Your weight, as you can see, acts on the floor. The floor feels your weight. You feel the normal force. And most people associate that normal force with what their actual weight is. But if you actually think about it, if you think about the idea of weightlessness, if you've ever stepped off a curb or you've ever jumped into a swimming pool or anything, or jumped from maybe bungee jump, something like that, when you're in free fall, people describe that as weightlessness. And the thing about that is you're not weightless. You have weight. Your weight has never gone away. It's never changed. But what has been removed is the normal force, what you typically feel as your weight, that reaction force. So it's important to realize that you have the weight, your force of gravity, but what human beings feel as their weight, which is not really a physical force, like that's not the weight of your body, but what you associate with your weight is this normal force. And again, when the normal force isn't there, you kind of have this feeling of weightlessness. It's like a feeling of falling. So what we have to think about is our normal weight is when we're just standing down. Most of the time, when we're standing still or when we're sitting in our chair, our force of gravity pulling us down is equal to the normal force. So that's what we kind of call our normal weight. What our normal force is, that's what we assume is our weight because it's equal. The net force on us is usually zero, at least in the y direction. So the normal force is that force of weight. In certain situations, the normal force will actually shrink, so gravity will be stronger. And again, even though your weight hasn't actually changed, your sensation of weight has, and because it's lower than what it was before, this is what we would feel as a lighter weight. Sometimes you get that kind of queasy feeling if you feel this on like a roller coaster or in an elevator, and that's because your body momentarily is not used to this lighter feeling. If we go the other way, if our normal force in certain cases is much higher than our weight, again, our weight has not changed at any point. We haven't changed our mass. But if the normal force grows for some reason, like an accelerating elevator or roller coaster, that will appear to us to be a heavier weight. So we'll feel like we're being like thrown or pulled into our chairs or the roller coaster or the elevator. And that all just comes down to normal force. So just realize that the force of gravity is in no way changing. It's the normal force is what we interpret as our sensation. Okay, so that will tell us heavier weight, normal force is larger than normal, lighter weight, normal force is less than normal, so to say, and our normal weight is when we're just standing there and our normal force is just equal to the force of gravity. Just to look at a quick example so you can have an idea of what this actually means. In this example, we have a cart with a mass of 150 kilograms, a velocity of 30 meters per second, and a radius of 10 meters. So the question becomes, will the rider feel lighter, heavier, or normal regarding their apparent weight? And I say apparent weight because that means the weight that they feel, not their actual weight, the weight that they actually feel. So the way to think about this is, if the normal force is less than gravity, you'll be lighter. If your normal force is equal to gravity, that's your normal weight. And if your normal force is heavier than gravity, you'll typically feel larger than gravity, you'll feel heavier. So if we look through here, we know that the centripetal force based on this situation, we have mv and r. So the centripetal force will equal 150 times 30 squared over 10, and that gives us a centripetal force of 13,500 newtons. We also know, since we have the mass, we can find gravity. So the weight acting on this object is 1,471.5 newtons. We don't know what the normal force is. That's what we're going to have to go ahead and find out. Well, if we draw a free body diagram, as we did earlier, you'll find that at that top, the gravity and the normal force from the track both point down. Therefore, Fc equals Fg plus Fn. So all I'll do is take Fc, Fg, which I know from up here, and I'll just plug them into this equation. So here's my equation. Fc was 13,500. We found that up top. My force of gravity, my weight was 1471. I also found that up top, plus my unknown Fn. If we solve for this, we can realize that the normal force is just 12,028.5 newtons. If I compare the 12,028.5 newtons to my force of gravity, my weight, you can tell it is significantly higher. Since my normal force of 12,000 is greater than my weight of 1,400, the rotor will feel heavier than normal. Their weight has not changed. They still weigh the same amount, but the sensation they will feel will be as if they were heavier because the normal force is significantly higher than what they're used to feeling. Likewise, we could apply this to like if you're going over a hill in your car, same situation. Let's say the radius of that hill is about 25 meters. Here you're given the mass and the velocity. It's the same process. Because we have circular motion, we know there's centripetal force, and we can certainly calculate that. We can also calculate the weight because we have the mass, and we don't know the normal force, we can find that out. In this case, in our free body diagram, gravity pulls the cart down, but the cart doesn't accelerate down because the roadway is pushing back up with a normal force. So my centripetal force here would be Fg minus Fn. Why is Fg positive? Because gravity is pointing towards the center of this loop. Why is Fn negative? Because here it's pointing away from the center. And remember, towards the center is positive, away from the center is negative. I will simply plug in the values that I know from up here. 2,000, don't know why there's two commas there, ignore that. 2,943 newtons minus the unknown normal force must equal 2,700. These values calculated up here. I find that my normal force is 243 newtons. My normal force is 243. My weight is 2,943. You should be able at this point to realize that the normal force is less than gravity, therefore the rider feels lighter.